Greetings, welcome. So I think I titled the video something like capacitor size, coil tau time, and Q factor, which is what we're going to be talking about. But what we're also really talking about is the inductive spike. So, by way of background, and not to say too much, but this stuff took me a while to figure out, and it was mainly the result of experimentation. And I remember back, after I first was basically like driven out of FDA, and instead of grinding my teeth, I came across the strange stuff that Tom Bearden and John Bedini were saying, and I was thinking to myself, they're not selling something. They seem very animated and earnest that they're saying something coherent, but I don't know at all what they're saying. So back then, I just figured, all right, well, let's make it a hobby. Maybe I can debunk them, and started off with like Forrest Mims' Introduction to Electronics in the Radio Shack's kit. How does a transistor work? It's really where I started, and I was also on the forum. I was keeping track of the forum that Bettini was on, that I think Aaron Murakami was looking at that at the time. And at one point, despite not knowing much, I'd been at it long enough that, there's all these people, oh, you need a low energy thyristor, and, you're never going to do it with that 555 chip, not unless you balance the load. And at one point I just said, look, there's only one thing changing here, and that's the coil, for the SSG. The coil, the current is changing, and you're getting the inductive spike. So how do you engineer for the inductive spike? How do you engineer for it? It was just crickets. It's like absolute silence. Nobody said a darn thing. I don't know. I think some of them were maybe like, well, I'm not going to dignify this with a response. And then, there were other people that knew a lot that were probably like, well, hell if I'm going to tell you. So I had to do all that myself. And so I guess because I'm kind of stubborn, and also, if I got any further on this, I probably might not say anything. But I'm right at a point where I can kind of disclose what I've learned over the years. Because as I said, if it got much more interesting, like getting into the Don Smith kind of level, then might not want to say as much, just being human nature as it is. I like people sometimes, some of the time, some people. But, so that's sort of neither here nor there. Another neither here nor there. I had an uncle named Don Smith. He's passed on now, but he was a judge in New Jersey. So I'm expert on the Don Smith stuff, just not the electrical engineering Don Smith stuff. Let's get down to it. Actually, even before we do that, I want to thank two commenters. One mentioned, when you make a pulse shorter, it makes things better. Well, yes and no and maybe, and that's what I'm going to go into and explain in this video. And the second person I really want to thank was, I was saying I'm having trouble just capturing small caps on a multimeter. He said, well, get an oscilloscope. And so I got this oscilloscope. That was the last video. My gosh, I've had the thing for like 2-3 hours that I've been using it, and I just freaking love it. I didn't expect that at all. I thought it was going to be like tedious and geez, it was utterly useless. It's like such a relief and such a great leap forward. So thank you to that person. This thing cost less than a laptop computer, and I haven't even scratched the surface of all the capabilities. I'm just scratching the surface. So we'll get into that, and this is going to take a while. You might want to grab a cup of tea. So I'll talk at you for a few minutes about what I've learned about the inductive spike over the years, and then I will demonstrate it also using the new oscilloscope and go from there. So we need to start at the beginning with fundamentals, and what is the inductive spike? Where does it come from? And it's sort of a question like, why is the sky blue? But it's characterized, it follows the pattern that Faraday discerned centuries ago now. And that is that whenever there's a changing magnetic field, an electric current appears. And so here's Encyclopedia Britannica and the actual relationship. The magnitude, Faraday's law of induction states that the magnitude of the electromotive force induced in a circuit is proportional to the rate of change with time of the magnetic field that cuts across the surface. And then they're also saying that EMF has units of volts. So the volts of your spike is proportional to the rate of change of magnetic flux. So to bottom line that, if you have a weak magnetic field that changes slowly, you will have a low voltage for your spike. If you have a strong magnetic field that changes slowly or a weak magnetic field that changes quickly, you'll have a moderate spike. And if you have a strong magnetic field that changes quickly, you'll have the highest voltage spike of all. That's what that equation tells you. Now there's a couple things that should kind of give one pause pretty much immediately. And the first thing is that this is a rate of change phenomena. In other words, if you have a constant magnetic field, there is no induced current showing up. So the rate of change of the magnetic field is not directly related back to the input current and voltage, the input current and energy used to establish the magnetic field, right? So in other words, you could put in energy, current and voltage, to establish a magnetic field of an arbitrary value that might collapse slowly or it might collapse quickly. And the inductive spike will be different depending upon the rate of change of the magnetic field. So that's the first thing, is that rate of change with time of the field is not directly tied back. It's not directly tied back to the energy used to establish the field, except for that the energy used to establish the field, you would think, well, that is going to determine how strong the field is. But the second point is that the strength of the magnetic field is also not one-for-one directly proportional to the input energy. And for a good read on that, I would recommend Joseph Newman's write-up on his big Eureka machine. But we can sort of make an obvious example of that if you have an electromagnet with 100 turns on it with a gauge of wire, such that when you put in 10 volts, 1 amp flows through those 100 turns, then you have a magnetic field strength in ampere turns, which is the unit for the B field, of 100 amp turns, because you had 1 amp going through 100 turns on your coil. Now, there's a few ways to look at it. If you just added another 900 turns, well, now what happens is your resistance has gone up tenfold, so there's only 0.1 amps going through, but once it reaches a steady state, you now have 0.1 amps going through 1,000 turns, and so you again have 100 ampere turn B field magnetic field strength. So the amp draw has gone to 1/10, and the magnetic field strength is the same. Or if you put 200 turns of wire on a coil, but you now increase the wire diameter such that those 200 turns also would allow 1 amp through at 10 volts, then now you've doubled the strength of the electromagnet, but you're still drawing 1 amp of current at 10 volts. So again, the strength of the magnetic field, which will determine the change of the magnetic flux, there's your magnetic flux from the strength of the magnetic field, is also not directly proportional to the input energy. So both of those things, should kind of make one scratch one's head. It's like, what the heck's going on here? But neither of them tell you anything about how to actually engineer for the spike. And quite obviously, it's not simply a matter of having a giant coil of 1,000 pounds and then it's going to be over unity with the spike, because otherwise all of the large transformers in the world would be over unity and they'd like blow up and the universe would dissolve, or something like that. Sorry. But it's clear then that there's a third factor coming into play, and it's related to the induction itself. So let's back up and again think about this at a very basic, almost silly basic level. And we know that the inductive spike is a rate of change phenomena. It's something that doesn't show up unless the magnetic field is changing. So what happens when you put a constant voltage into an inductor? Well, it starts off and there is actually a tremendous amount of resistance at the beginning, and the magnetic field begins to establish itself. As the magnetic field begins to establish itself, the resistance decreases in the coil until eventually the field strength reaches the strongest that it's going to reach for that particular coil. There's now a constant amp flow going through. So, to use a somewhat silly example, let's suppose that it takes 1 second for the coil to establish its steady state where it's fully saturated with current, and now it's the strongest it's going to be. So if you just ran that coil for 10 minutes and then at the end of 10 minutes shut it off, you would then get a little spike there, not a little, you would get a good spike there when the magnetic field changed and the coil went back to zero in terms of its amp flow. So let's again say it's a coil that at 10 volts is, once it's reached its steady state and is saturated, is drawing 1 amp. So you would put the current in and it's drawing 1 amp for 10 minutes, and then you shut it off and you get a spike. But you could also put it in for 1 minute and then shut it off and you would get a spike. And so if you're trying to gather energy off the spikes, the second approach would be 10 times as good, because you didn't just leave the coil sitting there with no change. Now, we said the coil fully saturates at 1 second. So now let's put it in for 1 second and then shut it off. Now that would be 60 times better than the one where you went 1 minute, and 600 times better than the other. Where it gets interesting is, what if you don't fully go to the coil being fully saturated? And this is where we introduce the concept of the tau time of a coil, which is analogous identically to the tau time of a capacitor with its RC constant. So I'm on the site Electronics Tutorials, just a wonderful site if you want to learn. And let's see what they say about the tau time, the time constant of an inductor. So here's the graph I was looking for. And so we see that 1 tau time for a coil under constant voltage is the time it takes for it to get to 63% of its maximum amperage that it's ever going to have. And that's the same as 1 tau time of a capacitor is the time it takes for it to get to 63% of the voltage that it's ever going to have. Okay, so we mentioned that, if you just left this thing on steady state for 5 days and then let it collapse, you would only get 1 spike. But you know, maybe you would do it 5 times a day and get 5 spikes. But here's something important is, so after 5 time constants, you're basically at the steady state. And what if you go to 4 time constants? Now you're going to be at, you know, maybe 98% of the maximal field strength you'll ever establish, but you used approximately 4/5 of the current, 4/5 of the coulombs of electrons to get there. Now what if you go to 3 time constants? Now you've used 1/3 less coulombs of charge to establish the field, but you're still up at like 96%. Now if you go from 3 to 2, well, that would be 1/3, that would have been 1/4. And then what if you go from 2 to 1, and you can see you've used half as much charge, but you still have 63% of the field, the magnetic field strength. I mean, actually, you've used less than half the charge in going from 2 to 1, because this part was a lower resistance part of the inductor, of the curve here. So you've used less than half of the coulombs of charge to establish a peak field strength of 63% of this. And that process goes on ad infinitum until you run into other issues. And I did a video about 2 years ago now, and I tried to watch it. It was actually astonishingly dry. But I think I've covered the whole thing now, but it was entitled Instantaneous Amp Flow or something like that. And what I did is I actually went through this, and you see you would need calculus to figure out the area under the curve for how much charge you exactly use to establish any given field strength. And what I did is I just sort of cheated with the spreadsheet and approximated. I mean, here's the expression for instantaneous amp flow in an inductor. And, you know, if I was like Tom Bearden or something, you know, oh, we'll just throw together an integral of that. But I can't do that. Maybe someday, but not today. And I wasn't able to before, so I was just approximating it by a spreadsheet. But what you want to do is integrate this curve, and then you would, you know, have it exactly. But what you can see just from a spreadsheet is that it continues on and on and on. Now, of course, that doesn't mean that your inductive spike gets bigger, you know, the faster you're going. The inductive spike is getting smaller and the voltage is getting lower, but the relationship between the amount of coulombs of charge you expended in order to get a particular strength of magnetic field as compared to the, as compared to, you know, the collapse for the spike is always improving as you're going down here until you run into other issues. And those can be issues with your components. You know, do they go fast enough, or you know, do they change at different speeds, or of course skin effect. It's a big one with the air core. And then if you're not using an air core, if you're using a ferrite core or something like that, then you run into a whole slew of other issues. And we can just group those all together as core losses, and note that some of the core losses often seem to change not linearly, but, you know, by a power of 2 or 3, depending on things like frequency and current. And I guess it was Steinmetz that really did a lot to illustrate and expound on and change the landscape of the understanding of how cores behave. I know that Eric Dollard's read a lot of Steinmetz, so I feel comfortable mentioning Steinmetz. The Wizard of Schenectady. So I'd said some time back, well, you know, someone said, well, quicker pulse is better. But that's actually kind of meaningless unless it's attached to a particular inductor. So what's actually of consequence is where you are on this curve. I mean, did you saturate so you could have, say, a 10 millisecond pulse, and you could have a core that saturates in 1 millisecond, in which case that 10 millisecond pulse is incredibly inefficient. Or you could have a core that saturates in 1/10 of a millisecond, in which case you're like down there on this graph. And it's as you get down in here that things get better and better in terms of Q factor, and hence in terms of your spike. So 2 more things, and then we'll just go and I'll illustrate some of this for you. And I also said, well, maybe, because then also when you start going fast, you start running into those other issues which might be mitigated or eliminated by coil design, such as we see with Tesla's kind of odd-shaped coils, or Litz wire, or however you want to try to approach those issues of going fast, as well as now if you have a core that's not an air core, then you have a whole nother, I wouldn't say it's a PhD, I'd say it's like a career to actually understand the behavior of transformer cores, the different materials and everything else. I mean, it's not like okay, now I got the answer. It's a big topic. So that's the maybe part. So the last thing I'd mention on the didactic part of this is, so you have your tau time here, and there's 1 tau time, 2 tau times, 3, 4, 5. What determines the tau time? And it's actually very simple. The tau time is the ratio of the inductance of your coil divided by its resistance. So it's L over R. I read somewhere, I can't remember where now, but I read somewhere where Tesla was saying, I'm looking at coils of high induction and low resistance. And so that would mean that as the induction increased and the resistance went lower, that for a given pulse, it would be better on this curve. Well, in a moment, I'll illustrate all this on the breadboard, but I have to just mention a couple other things. Is that even, this is a little bit complicated here. This is a pulse, with a power source of, say, 10 volts that's going into it. And so it's a constant voltage pulse. And, what you see here is the resistance is initially just incredibly high, and then it decreases until finally, when you get to the steady state, the only thing you have left is the straight line DC resistance of your wire. Now, if you're pulsing a cap into here, then you just added a whole nother layer of complexity, haven't you? Because now the voltage isn't constant, the voltage is decreasing. So I was talking about like trying to figure out, well, it's actually easier because you just let the cap go to 0. But this curve is for a pulse from a constant voltage source. And when you're discharging a cap into a coil, it of course isn't a constant voltage source. So that's like adding another layer of complexity. There are some things that are counterintuitive when you consider discharging a cap into a coil. So when you discharge a cap into a coil, what do you have? You have an LC tank circuit, right? Yes. And your capacitor will discharge into the coil and go to 0. Now the coil is filled with current. The current discharges in the opposite way, leading to a voltage driving the cap negative, and then it goes back up. And there's a particular frequency at which the cap and the coil oscillate. Now, what determines that frequency? What determines that frequency is the definition for the frequency is 1 over 2 pi times the square root of LC. And what's not in that equation? Resistance. So one of the things that's very bizarre is that suppose you had a coil of let's say 10 millihenries, and it has a resistance of 10 ohms, and now you change the resistance to 5 ohms. So there's half the resistance. The coil's going to discharge twice as quickly. No, it doesn't. The rate of discharge of the coil, which leads to the frequency, now, is determined by the square root of LC. And so it discharges at the exact same frequency, even if you made the resistance 1/100th of what it was before. The coil will discharge in the exact same amount of time. Isn't that bizarre to think about? That the resistance has no effect on how quickly the coil is discharging. Now, resistance does have an effect, but what it tells you is that the big boss is the dynamic resistance, this stuff here, and that the straight line DC resistance is negligible when you have a changing field that's oscillating all over the place, changing magnetic field. Now, the last part to that, and then we'll start to do the experiments. Tau time is defined as inductance over resistance. So what happens when you keep the inductance constant, but you double the resistance? Now your tau time is twice as big. And I think I use the example of making the resistance 100 times bigger. Now your tau time is 100 times larger. So that same pulse, even though it's the same amount of time, is 100 times further down on here, which is where you want to be efficient. So that's why I'm saying yes, no, maybe, because the pulse time is absolutely dependent on your coil. I mean, it's just that straightforward. Let's set some things up on the breadboard and illustrate this, and we'll also have fun with the oscilloscope. My gosh, I think it may be the coolest measuring instrument I've ever had. So let's just start with this random coil. I was previously using this thing to spin rotors, just something I had lying around, and it's 22 gauge wire. And it has 9.88 millihenries of inductance. And we'll start with these two in parallel, so that I'm not going to measure them, but they're both, by name, they're 10 UF each. You know, it could be 9.8 and 9.9 or something like that, but it's going to be about 20 UF. So let's jot that down. So we put that in a spreadsheet. We got 9.88 millihenries, 20 UF. The frequency, that 1/2 pi times square root of LC. And so that gives us our resonant frequency, which is 358 hertz. And the time between wave crest to wave crest then is 2 pi times the square root of LC, which is that many milliseconds. And then it would be that many for the thing to go as far negative as it's going to go. And then over here, I just threw something in. What this is doing for you is calculating how many milliamps you're up against. This is at 30 volts, so we're going to be at 10. Okay, so this is 10 millivolts. I'm sorry, 10 volts now, and that many milliamps. And I did that because sometimes I was frying these things and I thought, oh, you know, you can't go to like 30 volts or whatever. I was actually frying them. These are 500 or 600 milliamps, and I had no idea that I was going that high. But you know, at 30 volts we were getting close there with this coil. And that's because, you know, you have the cap and it's discharging to zero in, you know, a quick amount of time, and for that quick amount of time you can end up putting out like an amp or something like that before you even realize it. Okay, what's the tau time of this coil? The tau time, to get that, we need to know the resistance. So the resistance here is 5 ohms for this coil. So we said it was 9.88 millihenries, so that many henries, 5 ohms. So your tau time is that many seconds or that many milliseconds. Now we can already see from the that's wave crest to wave crest, but it takes that long for the cap to discharge. Or no, half of that time. It takes that long for the cap to discharge. So we're less than 1 tau time, but we're not really very far down along that curve where it starts to even improve more. So it probably won't be very good, but let's see what it does. So just in terms of the circuit, what do we have here? Forget about all the diodes. That's for the bitoroidal whatever. I'm not using any of that. All we're using is this switch, and one of those, this switch. This doesn't do anything. So what you have is you got your 2 bus lines coming in from the power supply. The positive goes to there, the negative goes to there. So you put a cap from here to there, and the cap charges up. And then you shut that off, the cap's just sitting there, and then you discharge the cap across the coil. So I said we wanted 20 UF, so 2 of these caps, and so they get charged up, and then it shuts off. And these are solid state relays, so it's all opto-isolated. Now if we put a coil between this leg and then out to that part of the switch there, when that switch turns on, the cap discharges around to there. And that's your LC tank circuit. So we'll do this the old-fashioned way first, and then I'll show you the glory of the oscilloscope. Okay, so we have it running like this without the oscilloscope. It just charges up, and then we see how far it discharges based on the calculated place where it'll be most negative. Let's get rid of this 2-second delay and get rid of this 1-second delay, and then hook up the oscilloscope. So I've just placed this meter across the power supply just to know exactly what the power supply is. So 3.78. Now here's what we got here when we're looking at that. So let's slow it down or look more closely at it. And that's what we see. So let's turn up the voltage now. And I want to put the voltage at 10 volts. Yeah, and that's why I have the meter there, because so now we have the power supply exactly at 10 volts. There's the waveform from this, where it discharges and then it goes negative, it's sitting there for a while, and then you're just charging it all the way back up. Now we could change that, but that's what it's doing now. But what we want to know is how far negative did it go? And that's where, before we were looking at it and saying, well, when we were at 3.6, it looked like it went to negative 2.6. Now we can start to have fun with the oscilloscope. So measure. Yeah, it's hard to get any of this to show up. Measure, and then we want to say voltage. And I'm interested in Vmin. That's what I want to measure. So I'm going to say add. And now we see down there, it says it went 700 millivolts negative. Now, this took me a little while to figure out, but this thing is 10 to 1. It's when it says 700 millivolts, it means that it's 7 volts, because this is on the 10 to 1 setting. I probably covered that in the video when I showed setting this up, that there's a 1 setting or a 10 mega ohm setting. So you have to times this voltage by 10 to get your actual voltage. So it went negative from 10 to negative 7. Now okay, it creeped up to 10.01. Let's put these back on here, and we'll slow it down so the meter can register and see what we get. I think I bumped the power supply there, but so it's saying 10 to negative 6.8. I think it's actually still measuring the same. I think I bumped that up without noticing. but maybe not. But I think I did, negative 6.84. So 10 to negative 6.84, and let's go back once more to just the oscilloscope. Okay, we're at 10 volts again, and it's saying it's going negative about 7 or 7.2 volts. Which that's not bad. I mean, it went from 10 down to negative 7.2. Now, it gave us the hertz here. This isn't the hertz of the actual oscillation. This is the hertz of it's going down to there, and then we're just cutting it off and recharging it as quick as we can. So it's the hertz for that cycle. You can see this leg looks different than that leg. But what we can do is let this thing run for a while, and we can observe how quickly it dampens out. So it gave us that hertz, like 412 point. Well, actually, that's probably not what we want. Sorry. But the hertz from wave crest to wave crest is, from the spreadsheet, 2.79 milliseconds. Just bear with me. This will be pretty cool. And then we'll demonstrate the improvement with a shorter pulse with the particular coil. So if we do 12 of those, that'll be 12 oscillations. And so that's 33 milliseconds. So let's throw that in the code. We'll call it 34. So that's what this LC tank circuit looks like after 12 oscillations. It's pretty much gone. It's just damped out entirely. 1, 2, then nothing. Okay, so, you know, when I was doing this, for some of them, I was going like 20, 10, 4.7, 2.2, 1 point, 0.47, 0.22. Let's just jump from 20 to 4.7 and see if we get an improvement in the Q factor, all right? So if we go back to the spreadsheet and we throw 4.7 in there, now we see that the frequency is 738 hertz and about 677 to when it's most negative. Now, one of the glories of this thing, when we look at it again, if we go back to our code, we're saying that it's calculated at around 677 microseconds is where the thing goes most negative. But the cap might be 4.6, and the measurement might be off a little bit. Doesn't matter now. All you have to do is, let's set this at 750. So now it's going to go negative, it's going to go back to there, and then it's going to charge up. But the oscilloscope will measure for us the difference between the highest and the minimum. It'll give us the minimum voltage. That's all it's doing, is giving us the minimum voltage, Vmin. So you just make this longer, and then you know that you reached the minimum voltage. Instead of, when I was doing it here, like sitting there fiddling around trying to find, well, is that the most minimum? Is that the most minimum? Is that the most minimum? Now you just make it longer than the most minimum, and this thing will tell you for us. So I think it said 676. I'm going to make it 800. And we don't want to run it as a bell ringing, so we're going to, we got rid of the delay on time already. So if we recalibrate, so you can see on the oscilloscope what I'm talking about. So this is actually that 500 microseconds. It's just showing the cap has plenty of time to charge. I mean, we could make that like 200. That's just the cap is charged, and then it discharges. It goes as negative as it can, and we let it go further, so it's starting to go back up. And then at that point, we said, all right, charge back up. And that's why this is such a direct line as opposed to this one, nearly vertical as opposed to this one. But it gives us the most minimum value. And the most minimum value now is 8.2. 820 times it by 10, 8.2. It went from 10 now to negative 8.2. And that's because of this. So with the 20 UF cap, we went to 7.2, negative 7.2. With the 4.7 UF cap, we went to negative 8.2. higher Q factor, better spike. Now, what I forgot, so this, it took it 676, it took it 338 microseconds to discharge the 4.7 UF cap. It took 338 seconds. Now, if we go back to 20, that took 698 microseconds for the cap to discharge. So shorter pulse, better, but it relates to your core as we're going to your, not your core, your inductor, as we're going to see in a minute here. So let's just do one more thing with this coil, and then we'll switch to a different coil, and I'll show you how a different coil behaves. But before we let this thing ring, just let it ring for 12 times. We saw how quickly it damped out. Now this is a bit better, 7.2 to 8.2. So it takes it 1.35 milliseconds to go from wave crest to wave crest. So let's do 12 of those again and see what that looks like on the oscilloscope. So we could go a bit smaller with the caps with this coil, but we'll go to a different coil. But this is that cap and coil ringing 12 times. Now you remember the last one, it was basically you couldn't see anything from there. So this is a bit less damped, isn't it? And we noticed that also because instead of going to negative 7.2, it went to negative 8.2 or something like that. I'd have to check exactly what we said. But you can see it's less damped this way as well. Now, I won't bore you with it. If I put the meter on this 4.7 UF cap, we won't be able to, let's see what I said. Said it went to negative 8.2. It would register like 7.8 or 8, and it would be all over. Like one time you'd see 8.1. Did I see 8.15? No, it's 8. No, it's 8.05. It just can't, it can't go. About 10 UF is the best you can do, and you can try and get 4.7 UF on there, but that's all you can do. Whereas with the oscilloscope, both because it's sampling 1,000,000 times a second and because you have a 10 mega ohm resistance here instead of 1 mega ohm, we can go smaller than 4.7. We can at least go down to 1, and I think we can go down to about 0.1. But let's go to a different coil, and I'll demonstrate what I meant by, the time is in relation to the tau time of the coil. So the pulse time, means something, but it means something only in relation to your coil that you're using. So let's do that. So let's look at this big daddy coil that's taught me so much. And we see that the inductance is approximately 91.6 millihenries as opposed to, it was about 9.88. So about 10 times the inductance. So the resistance of this big daddy coil here is about 5.6, 5.7, I'll call it 5.6 ohms. So therefore, with the measured millihenries, that the tau time is that many milliseconds, 16.33. The tau time of the previous coil was 1.976. So what I've done here on the spreadsheet, on that first coil, 1.976 tau time and 9.88 millihenries. Let's say we went back to the 20 UF cap. It's 1.39 milliseconds to get to the most negative. And that 1.39 compares to a tau time of 1.976. Now let's put 20 UF into this one. Takes 4.24, so like 3 or 4 times longer in order to get to the most negative. But that 4.24 is up against 16, so like 1/4 of the tau time versus like 80% or 70% of the tau time. So how far negative will this go with 20 UF, and then we'll go to 4.7, we'll go a bit lower. All right, so here we're running this with the 20 UF through here. Now what we see is it's going from 10 down to -9 volts. And it's at 10.01, sue me. I mean, it's hard to dial that in exactly right. So if we go back to the spreadsheet, we can see with the small coil, when it was at 20 UF, it was 1.39 microseconds for it to go most negative. This is 4.24 microseconds for it to go most negative. But that shorter pulse went to 7.2. This one goes to 9. So that's why I'm saying when you say shorter pulses are better, well, yes and no. I mean, it has no meaning outside of the coil. So to confirm this is better, let's let it ring again 12 times and see what it looks like. So there is the ringing for 12 times of this cap and coil. And you can see that it's better than the 4.7 UF even. I mean, it's still not great, kind of a bugle thing going on there, but it's getting better. So now I've stuck in the 4.7 UF cap. We see from the spreadsheet it's about 2 milliseconds for it to go entirely negative, so put in like 2100 microseconds to make sure we capture the most negative part. And what do we see? What do we see? We see that it's now flipping about 9.4 millivolts, 9.4 volts negative from 10. So let's throw that in the spreadsheet, shall we? 9.4. And the thing I would also reiterate, this pulse at 2 milliseconds is still longer than the 20 UF, and this is a 4.7 UF. Still longer pulse than this one, which would be at 1.39. So again, it depends on the cap and the coil. But now we're down to 10 to -9.4, and let's look at how it rings. So again, each time I'm letting the cap just ring 12 times, and now it looks like that. So that's a lot less undamped than before, isn't it? And that's because we went from 10 down to 9.4. So now instead of a 4.7, let's go to a 1 UF cap. So I've gone to a 1 UF cap, and now we see it goes from 10 to -9.6. And again, let's let it ring 12 times just to see what it looks like as a bell. So that's now what 12 rings looks like. That's pretty undamped. Can we go any further? And the problem you have is there's still 10 mega ohms across here. Now, this is 1 mega ohm, so this is 10 times better. But when we start getting down to like a 0.1 UF cap, you're still going to be leaking out across this 10 mega ohms. Let's try a 0.47 and see if we do a little bit better, and then we'll wrap this up. Okay, for the grand finale, I went all the way down to 0.1 UF. I doubt you can go much lower than that. I realize that the thing's sampling, a million times a second instead of like once every 1/10 of a second with the meter, but you still got that 10 mega ohm drain, and when you have that small cap. But long story short, 0.98. So it went from 10 down to -9.8. And let's just look at how it rings. So when we let it do its bugle thing and go 12 times, now that's what it looks like. Looks a bit different than the very first one we started with, doesn't it? All right, well, sorry for the lengthy video there, but that's how you improve Q factor. And can you go further? I think you can. I mean, there's you hear about things like the crystal radio sets and things like that, so I think you can go even further with Q factor, and I may return to that issue at some point. It seems, from what I've presented here, it seems obvious what the paths are forward to continue to improve it. However, I'm not going to work on that at the moment because I have something that works there with the Thane-Hines bitoroidal. I have a working bitoroidal transformer, and part of why I was doing this just with the oscilloscope and all is the way I have it set up. The higher Q factor you have on the primary for the bitoroidal, the better the thing is going to work. And it's a whole different animal. As I said, it's got a core. So not an air core. It has a core, so it behaves differently. I don't want to ramble too much here. So I thank you for coming along. And again, that's how you improve your inductive spike. What I hope to try to do going forward is, just have some like fun videos that I'll have fun making that are more like for general audiences, like, hey, let's have fun with the Jewel Thief, and just build one and maybe put it on the oscilloscope, rather than these, like trying to be the professor from Back to the Future kind of thing, 18 gigawatts, Marty. And also continue with the health stuff, because I think, given my background, that's an area where I could be helpful as well. So, maybe one of these like every 2 weeks to a month as I work on things, and I'll try to get out just some like more fun stuff as well. So thanks again for coming along, and stay healthy, everyone. Take care. Ciao. Bye.